Hi everyone. In this project, I implemented a feed-forward neural network using the backpropagation algorithm that can perform the classification task of iris dataset. So while implementing, we have used three different like hidden layers. So at the end, we are comparing the results. So in the first one, I defined the four input layers, three three hidden layers, and output will be three neurons. In the second one, input layer is four, hidden layer is six, output will be three. And in the third one, the input layer will be four neurons, and the first hidden layer we are increasing the number of layers, hidden layers. So first hidden layer is 5, second hidden layer is 7, and output will be 3 neurons. So uh, the code is organized in several sections. First, we import necessary libraries and load the dataset. Then we define the generic neural network class to handle the forward propagation, back propagation, training, prediction, and finally the main section, the main function or the class or method uh, ties everything together by loading the data, creating the network instance, and training them and reporting the results. In this, first we need to load the data. So here we load the iris data using the scikit-learn, and notice that the target labels are reshaped to a column vector so that the one-hot encoding works correctly. We use the updated parameters sparse output false to get the dense matrix. The processing step is crucial to prepare our labels for multi-class classification with the neural network. So in the second section, the data set is split into training and testing set based on the predetermined indices. This ensures that for each class, a fixed number of samples is used for training and the rest for the testing. Splitting the data uh, Splitting the data in this way helps maintain a balanced set of model evaluation. So when we come to the our neural network class, so we have the construction. So this is the construction for us, and this constructor accepts a list of this that defines the number of neurons per layer. So this design makes the class flexible, allowing different architectures. So we use the initialization to scale the weights properly, and biases are initialized to zero. This setup helps in maintaining the good initial condition for training. So second thing is in the like forward method. The forward method, we compute the activations for each layer sequentially. The hidden layers are used the sigmoid activation function, while the output layer uses softmax, which is ideal for like multi-class classification. And this method returns both the activation and the intermediate weighted sums like ZC, this one, and which are later used in like backpropagation. So the backpropagation method implements the backward method implements the backpropagation. It calculates the gradient of the loss function with respect to each weight and the bias. The error is propagated backward from the output to the input. So applying the derivative of the sigmoid function at the hidden layers, this gradient computation is critical for updating our parameters during the training. The training is performed using full batch gradient descent. For each epoch, we perform forward propagation, compute the gradients via backpropagation, and update the weights and biases. The learning rate determines the steps for these updates. This loop continues for a set number of epoch to minimize the loss function. So the predict method is this one. The predict method uh, uses the forward propagation to determine the output class for each input. The accuracy The accuracy method compares these predictions with the true labels and calculates the percentage of the correct prediction. This provides the simple metric for evaluating the model performance. And when we come to the main function, so the main function is entry point for the program. So it first handles the data loading. So as I showed in the beginning, so it is handling the data loading section, and uh, and the processing. So then set up the network architecture by defining the list of for each model layers. So three network instances with different architecture. Each network, I mean, this in the beginning I have explained. So each network is trained individually with the training time recorded to give to give an idea of computational cost. Finally, we calculate and print the training and testing accuracy in a formatted table for easy comparison. So here we are like recording the starting and how much time it consumes. Okay, so that's it for me. Let us run the code and let us see the results. Yeah, as you can see, when this is our print section, so this is the results after the running the code. So this is the training accuracy, this is testing accuracy, and this is the time, the cost of the, I mean, you can say the cost. So training time. So as you can see, for ANN1, it is around 98%, this is 97%, and this is 94%. And testing accuracy is 96, 93, 94. So ANN1 is performing better. And when we see the training time, so training time in ANN1 is lesser than the other ones because it has, as we can see here, this is using for layer input layer neurons, and this is using 3 neurons, but here we are increasing the number of neurons, here we are increasing the number of layers, so it is increasing the cost actually. So that's it for me. Thanks for watching.